This example, we're going to find all 4 zeros. Since it's a 4th degree, there are going to be 4 zeros. But since this is next to the 4th, and there's 5 terms, we don't have any tricks for factoring or anything like that. So let's start by looking at our possibilities. So we take factors of the back over factors of the front. So it's 4 over 3 and all of its possibilities. So the factors of 4 are 1, 2, and 4. Factors of 3 are just 1 and 3. So we could have 1, 2, and 4 over 1. And we can have 1, 2, and 4 over 3, none of which would reduce. And all of these could be positive or negative. So that's 6 possibilities. And we just check them with synthetic division. So I'm going to start with checking 2. And that goes into 3, negative 2, negative 1, negative 12, negative 4. Bring down, multiply, you get 6, add, you get 4, multiply, you get 8, add, you get 7, multiply, you get 14, add, you get 2, multiply to get 4, add to get 0. So we do have a remainder of 0, which means 2 is a 0. And also you can notice here that these are all positive, which means there's nothing larger than 2, so positive 4 is not going to be a 0 either. You can also notice by looking at this, there's only one sign change. It starts positive and then goes negative and stays negative. There's only one sign change, which means there's only one positive 0. So there's nothing else positive. And since when we divided by 2, we got everything was positive, there's nothing greater than 2, like we said. So now the only thing left to check is the negatives. So I'm going to take a guess and try negative 1/3. I'll tell you why in a minute. So if you do synthetic division now with negative 1/3, do that to the solution, so that way we keep breaking down our polynomial more and more. So bring down the 3, multiply by 1/3, you get negative 1. Negative 1/3 times 3 is negative 1. Add, you get 3. Multiply, again, that's negative 1. Add, you get 6. 6 times negative 1/3 would be 6 over 3, which is 2, and so it's negative 2. Add, you get 0. That was the last thing, so we have a remainder of 0, so yes, negative 1/3 is a 0 of the polynomial. And to this 3x to the third, 4x squared, 7x plus 2, negative 1/3 is also a upper bound. There's nothing larger than negative 1/3 because everything was positive after we divided. Also, there was no sign changes, so there's no positive roots. Now, if you're wondering why I first chose to divide by 2 instead of 1, and then I next chose negative 1/3, I cheated a little bit and looked at the graph. So here's the graph from the graphing calculator. You can see that it looks like it crosses at 2, and it crosses somewhere between 0 and negative 1. And if you zoomed in a little bit, you could see that it's pretty close to negative 1/3. That would be the best guess from our possibilities there. There's no way of anyone seeing what you've done and knowing that if you're just a really good guesser, or if you got some help from a graphing calculator or something like that. So if you have a graphing calculator to use, you can use it to make your problems go a little bit quicker. So now that we have it down to 336, that's 3x squared plus 3x plus 6. We want to try to factor that further. So you can start by taking out a 3. There's nothing that would multiply to be a positive 2 and add to be positive 1, so we'll do quadratic formula. So negative b plus or minus the square root of b squared, so 1, minus 4 times 1 times 2 is 8, over 2a, which is 2. So that's the square root of negative 7. So negative 1 plus or minus I square root of 7 over 2. It's all over 2, so negative 1 over 2 plus or minus I squared of 7 over 2. There's our zeros from the quadratic formula. If we were just to write it out factored, you could do so as well, but the problem asks for the zeros. So there's 2 of your zeros because it's plus or minus. X equals negative 1/3 was also a 0. And x equals 2 was also a 0. So it was a 4th degree polynomial, so here's our 4 zeros. 2 real, 2 imaginary. And if you look at the graph, only the real zeros show up. So you still need to know how to get the imaginary zeros. One thing you might have started to notice was that every time we had a complex 0 show up, its conjugate was there as well. If a plus bi was a 0, so is a minus bi its conjugate. And that's true as long as it's real coefficients. There's no imaginary numbers in the polynomial to begin with. So let's take a look at an example that we can apply that. Degree 3, integer coefficients, and has zeros of 1/2 and 3 minus I. They only give us 2 zeros, but it says integer coefficients, which means its conjugate is also there. So if 3 minus I is a 0, so is 3 plus I. So x minus 1/2 is a factor. X minus 3 minus I is a factor. And x minus 3 plus I is a factor. So let's start by multiplying our complex numbers together. First, distribute the negatives here, so it'll be x minus 3 plus I and x minus 3 minus I. And a little trick to actually make the multiplying easier is if you think of the x plus 3 together, or x minus 3, x minus 3. Now these are a difference of squares. We have something plus I and then the same thing minus I. So that means the outside and inside stuff will cancel out, and let's treat x minus 3 as if it's just one number. So it'll be x minus 3 squared. Outside and inside cancels out, then it will be minus I squared which is negative 1. So cross it out, change the sign. X minus 3 squared is x squared minus 6x plus 9. And then we have plus 1. So that's x squared minus 6x plus 10. That still needs to be multiplied by x minus a half. If that shortcut doesn't work for you, then don't group it. Just multiply x to everything, multiply the negative 3 to everything, and then multiply the I to everything. You'll have more combining of like terms, but it'll all cancel out. You'll get the same answer at the end. So now when we multiply these together, we get x times everything is x to the third minus 6x squared plus 10x. Multiply the negative 1/2 to everything. That's minus 1/2 x squared plus half of 6 is 3x, and then 1/2 times 10 would be 5, so minus 5. Combine like terms, x to the third minus 6 1/2, or you could say 13 halves, plus 13 minus 5. And there's our polynomial function. Except the problem says integer coefficients, not just real. So we're not allowed to have any fractions here. So to get rid of the fractions, you just have to multiply everything by 2. So that would actually have to be 2x to the third minus 13x squared plus 26x minus 10. There's our final answer. For our last example, we're going to factor this. What multiplies to be negative 8 and adds to be 2. So we can factor that to be x squared plus 4, x squared minus 2. X squared minus 2, that is a difference of squares. It's a little bit different to think about, but what multiplies to be 2, but is the same thing, would have to be x, and then the square root of 2 times square root of 2 is 2, and if you add square root of 2 and negative square root of 2, it would cancel. So it's actually x minus the square root of 2, and x plus the square root of 2. And then there, with a sum of squares, there's a trick as well. If it's easily factorable, but it's just a plus, if it would work if there were a minus, that would be x plus 2 and x minus 2. The only thing that you need to remember if it's a plus is it's going to be imaginary, but that 2 is still going to be there. But since it's a positive, they need to be imaginary roots, so it'd be 2i and minus 2i. But there it is, factored.